everyone, and welcome to the second episode in the Introduction to Logic series that I started doing last week. Today, we are going to be covering proof by induction, truth functions, disjunctive normal form, and expressive adequacy. So if you've not seen the first episode, it will be linked in the playlist, which this video is a part of. So if you want to go back and cover any of that stuff before moving on to that, feel free to do so now. If not, we'll plod on with this. Hopefully, I won't make many mistakes, but I am a little bit tired. It's 9:30, so maybe that'll happen, but hopefully not. It's just that I do this live, and so, things go wrong when you do stuff live, right? Rather than pre-recording it and editing it out. Anyway, so proof by induction. This is basically going to be a useful form of proof that we're going to use in order to prove general things about our logic, our system of logic that we've created. So proof by induction is a particular form of proof. And to introduce you to the kind of main idea behind it, suppose that we have infinitely many objects lined up. So within those curly brackets, which mean like a set of a certain number of things, we've got an infinite number of these dots all lined up like so, which you can see. Which you can see here, right? And so we want to show that each of these objects has some property. So how would we go about showing that each of these objects has a property? Well, we could do a proof by induction. Proof by induction is comprised of two main parts. So we've got this first step here. This first step is going to be called the basis, or our base case. And then we've got this second step here, which is going to be, our inductive step or our inductive hypothesis. So what we do in the first case is we show that our first object has the property, or in general, if you're coming from a maths background, it'd be, showing that in our kind of first element in the set has that property. So if it was the natural numbers, it'd be the smallest natural number. People may be coming from a software or computer science background. You can think of this like in a recursive algorithm, like the smallest kind of unit that gets bounced up through the function calls or something. But in this case, it's going to be our first little circle here. So we show that has the property, and it does. So we've circled it in red. And then our inductive hypothesis is to prove this conditional, right? So the conditional is of the form if P, then Q. So you can see the statement show if an object has it, then the next one does, right? If an object has the property. So what we do to do that is we assume the antecedent of that conditional. So we assume that an object has it. And then from there, we prove that the next one does. So this whole inductive, our inductive step, when we try to show that's like a direct proof that's nested within our overall inductive case. So you can see that if we prove that conditional holds, then it follows, if any of these objects has it, then the next has a property, then the next one along has the property. So if that conditional holds, basically, it means that everything in the set has the property. It just bounces along. The conditional ensures that the truth of that property kind of like bounces along every single element that's in the set, like so. Okay, so one place that we can use this then, and this is, perhaps not too useful an example, though this sort of proof could be useful if you were writing, if you were writing a programming language or something which wanted to prove that if you could prove this about the syntax of your language, then something like this might be a good way of hunting for valid formulas or something. But what we're going to prove is that every well-formed formula in our propositional language has an equal number of left and right brackets. So you can, if you can't remember from the first episode, this is the definition of our grammar of our propositional language. So well-formed formulas are defined by any sentence letter, so A, B, C, and so on. And then any of these things in clause 2 of these forms. So we've got, not, and then some well-formed formula, phi and psi, phi or psi. Then we've got phi then psi, and phi if and only if psi, and nothing else is a well-formed formula. So this exhaustively this set here this part of the definition here basically exhaustively defines all the ways that we can connect things. Okay, so how would we go about proving this theorem that every well-formed formula in our propositional language has an equal number of left and right brackets? Well, firstly, think about what's our smallest case going to be that we can prove it for? Well, that's going to be this part here, the sentence letters of our language. So the smallest well-formed formula, sentence letters, are what we're going to prove it for in the first case. So we let phi be equal to a, just some sentence letter. And then we show phi has 0 left and 0 right brackets. 0 is 0. So atomic formula have an equal number of left and right brackets. So our theorem that every well-formed formula in LP has an equal number of left and right brackets holds in the case of our base case for the smallest formula for sentence letters. Okay, so now we're going to take our inductive step. And the way that we go about our inductive step is going to be proving some kind of conditional that propagates over every well-formed formula that we can construct. So we assume phi is a well-formed formula in virtue of our definition. Okay, so let me see what I've written. Assume that the statement of the theorem applies to the formulas alpha and beta here. So the statement of the theorem is that the number of left parentheses is equal to the number of right parentheses. So for alpha, we're going to call this number k, that the number of left parentheses and the number of right parentheses, and we're going to say that it's n for beta. So then if phi is a well-formed formula, so if phi is a well-formed formula in virtue of DF, then phi is either going to be constructed by any of these cases. So these cases exhaust what could be a legitimate construction in our grammar, by what's defined here in the second clause of our definition of a well-formed formula. Okay, so we're going to have to look at each individual case basically and show that for each case, the conditional that we're trying to prove that it has an equal number of left and right brackets holds. So in the case of not a, the number of left brackets is just going to equal k, the number of right brackets is going to equal k, and so we have an equal number of left and right brackets because k, because the left and right hand number of brackets are both k, right? In case the same number. So we have here for alpha and beta, which is this one, to beta, phi and psi there, or alpha and beta down here. So we have in our alpha case that the number of left-hand brackets is going to be k plus 1. So that's because we're adding that bracket. The number of right-hand brackets is going to be... This was a bit silly, actually. I'm going to erase that because what I didn't think of... Let's rethink. Because what I didn't think of is... You see how I defined that as k and that number as n. So it's actually going to be that our number of left-hand brackets equals k, which is the number of brackets that we have in the number of left-hand brackets we have in alpha. And then it's going to be k plus n, right, which is the number we have in beta, and then plus 1, which is this one over here. And then if we go to look at the number of right-hand brackets, okay, we're going to have, again, k plus n plus 1, and that's that one on the right. Okay, so we can see it's k plus n plus 1 for left and right, so the number of left-hand brackets equals the number of right-hand brackets in that case. And I mean, you can probably see it's going to be the same for each of these, but let's just walk through them each again. So in this case, alpha, we've said, let's count the number of left-hand brackets first. Well, alpha we know has k as its number. Beta has k as its number, has n as its number, sorry. And then we've got 1 added in here to make it a well-formed formula. And then the number of right-hand brackets is going to be k again plus n plus 1. So that's the same. And then that's just going to be the same in each of these cases. We don't need to show that. But what we have shown then is that if everything that, or if all of the smaller well-formed formula that we're constructing out of have this property, right, have this property of having an equal number of left and right-hand brackets, then any formula that we can construct out of them also has that property. So I've written out in blue here, for example, if we have well-formed formulas which have the property of our theorem, right? So remember, the property that we're trying to prove in theorem is that every well-formed formula in our language has an equal number of left and right-hand brackets. So if we have well-formed formulas which have that property, then any well-formed formula that can be constructed by connecting these well-formed formulas have the property in theorem. Okay, so when we combine that conditional with our base case that we already proved up here, that means that we've proved that every single syntactically valid well-formed formula that we can form in the language, because nothing else is a well-formed formula, has that property of having an equal number of left-hand and right-hand brackets. So hopefully that shows you how you can apply this general form of proof to kind of find things out that are going on in your logical language. And that is going to be useful when we come on to proving some things about, will we use it in soundness and completeness proofs later on? I think that I'll probably cover those in the next episode, but the form of the proof is going to be important. Okay, so now let's talk about functions, okay? So I've stolen this definition from Susan Epps' what's it? I think it might just be called discrete mathematics. But if you don't know what a function is, then a function f is basically a mapping from a set to another set, saying here a relation, relation mapping with a domain of A and codomain B. So you can see here we've got two sets, one of which is A, the other of which is B. And what the function does is it relates elements in A to elements in B. So for every element x in A, there is an element y in B such that xy is a subset of of f. So what is an element, of f. So what you can see here is every single element that's in A has a mapping, right? So there isn't an element over here that just stands undefined. Every single element over here is defined as having a mapping or being related to another element in B. But not everything in our codomain is necessarily has to be mapped by a function. Okay, so in this case, you can see that all of the, not that last item, all of these items here, they actually are not related in this position to anything that that our function f maps, and that's okay. We can call this set the things that are mapped, the range or the image. Those are other terms that you might hear, but the whole set is called the codomain, and that's going to be this kind of rudimentary understanding of functions is going to be useful as we come to talk about truth functions now for our semantics. So a truth function is a function whose domain is a set of sequences of truth values and whose range is a subset of the set of truth values, i.e., TF. So a truth function is going to take as its arguments, it's a function which is going to take as its arguments some truth values, and the answer that it spits out, or the thing that it maps to, is going to be a truth function, either true or false, one or the other. So you can see a few conjunction, disjunction, and negation as truth functions kind of mapped out here. So, for example, in the case of conjunction, when both of the argument places are true, it spits out true. When one's true, one's false, you get false. Same for false truth, and false false spits out false. Disjunction, all of the cases in which one of the argument places is true, at least spit out true, and then when they're both false, you get false. And negation, there you can see that you get the opposite. So here's a definition then of a truth functional propositional connective, because we want to talk about our connectives in our language. So those are, like and, or, if then, the biconditional, these sorts of things. A truth functional propositional connective is a meaningful expression or symbol that can be combined with propositions or formulas to form propositions or formulas, and can be completely defined by a complete standard truth table. So if you recall from the last episode all the way up here, when we were talking about, like the truth tables for and, for example, or the truth tables for if then, well, that is basically a different way of representing what the function does, what the truth function does. So you can see that that last column in the truth table for and, for example, is exactly the same as that, or the last row, the last column in the disjunction truth table is that, for example. So a truth table is basically an expression of a truth function, right? So our next topic then that we're going to come on to is disjunctive normal form. So disjunctive normal form is a way of writing out a formula. So it's basically just a form. There's weird stuff going on in the chat. I'm going to just try and ignore that and focus on this. So a formula is in disjunctive normal form if and only if it's a disjunction of conjunctions of single propositional symbols or their negations. Okay. So what does that mean? Well, these are all some examples of formulas that are in conjunctive normal form. So you can see it's a disjunction. So see these disjunctions here. A disjunction of conjunctions. I'm going to do these in blue. Didn't mean to do that one. That's not a conjunction. Of single propositional symbols or their negations. So, these things, as you can see. So the reason that these are examples then, taking this first one, is because you've got this conjunction, right, which is this thing here, P and P dash and not P dash dash, or P and P dash. It's there's nothing really significant that hangs on this, except it's just a particular form of writing out a sentence in our language for now. So here's another one. We've got not P and P dash, or P and not P dash, or not P and not P dash. Other interesting cases, P or P dash, that is also going to be in DNF. P and P dash, that's in DNF. P and not P dash, that's in DNF. And the reason I say that this one is interesting is because you'll notice that these are the same sentence letters. So that's actually an outright contradiction. So every single, the truth table for that, everything is going to come out false, basically. And then in this case, not P just on its own, or I suppose P just on its own as well. Both of those would be in DNF also. So DNF is going to be important because it's going to play a role in a proof that we want to do for something called expressive adequacy. So what is expressive adequacy? Well, a language is expressively adequate if and only if it can express any truth function. So our truth functions that we've just introduced above, a language is going to be expressively adequate if for any every single truth function that there is that exists. So any function that takes truth functions as its arguments and spits out true or false, returns true or false. Well, language is expressively adequate if absolutely everything of that form can be expressed by it. So if there's anything that can't be expressed, any truth function that can't be expressed, our language isn't expressively adequate. So another way of putting that is for any truth table that can be completed, there is some way of expressing that truth table in our language. So, if we've got truth tables, if you give me any truth table, right, it can be true, 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 false, 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 false. That's trailing off a little bit. I don't know why do I do silly things like this when I'm live? It can be, true, true, false, false, true, false, true, false. It can be in that form. And basically anything that any combination that's going to appear in that last column for our function. So it can be, true, false, true, false. Well, if this and all other things that might appear in that last column can be expressed in our language, then we have an expressively adequate language. But if our language can't express this, if we've got truth functions that there are truth tables for which we can't express in our language, right, then we don't have an expressively adequate language. It means that our language doesn't capture all the possible truth functions, and that's just what it's supposed to do. So this is a meta theorem. This is a theorem that belongs to meta logic, right? It's not within the logic, but it's about our logical language. And we're going to show that the set of connectives that includes not, that's not, and or, is expressively adequate. So let f be any truth function with an arity of n. So arity is just the number of arguments that it can take, true or false, for going in the function's argument places. So the number of those arguments is going to be n. And so a completed truth table for f will have n plus 1 columns and 2n rows. So suppose that we have 2 arguments, right? Then the truth table is just going to be look like this. We're going to have 1, 2, n plus 1, 3, right, for our function, that final column, and 2 to the n rows, so 4 rows. Well, that's basically just like this that we drew out before. Similarly, if we had another variable, if we had, p prime and p prime prime, then we have f on the end. So we've got 3 arguments, or our truth function has an arity of 3. And so we have 3 plus 1, which is 4 columns. And the number of rows that we'd have would be 2 cubed, which is 8. So we'd have, 8, 1, 2, 3, 4, 5, 6, 7, 8, blah, blah, blah. You get the picture. So that's all that part says of this proof. Okay, and so there are 3 possibilities for our last column, and I'll just draw out the basic truth table then. So there are 3 possibilities for our last column, which is the one that has our function's values in. Okay, and those options are everything being false, right? Firstly, secondly, there's exactly 1 true row in the last column. And thirdly, there's more than 1 true row in the last column, okay? So our first case can be expressed as p prime and not p prime. So you see that that's a contradiction. And then we just conjunct that contradiction with every other value that there is up to, p with n number of primes. And that's going to always come out as false. So that satisfies our first case. I'll use different colors for each of these cases. So, okay, now in our second case, exactly 1 t in the last column. So for the row that has t in its final column, so that would be, let's say we've got this, true, true, false, false, true, false, true, false, and we've got, true, false, false, false. Well, that's clearly that row. We're going to read off the value in each formula column. So here, those values are, where's my highlighter gone? Those values are p and p prime. If it's t, we write p with its value number. If it's false, we write not p. So we're going to get, p, and we're going to get p prime. And then what we do is we form a conjunction of all of those. So you can see how that would go, if we had more, or let's say instead, it was this row, that was the true one. Well, what we do in that case is we would have, our first one would be not p, our second one would be p prime, and we just AND them together like that. Okay, so thirdly, for each row that has our third case, I'll use a different color, blue. For each row that has a T in its final column, we form a conjunction of that row as in case 2. So just like we did before, we go along the row, we read off each value. If it's false, we negate it. If it's true, we just assert it and we conjunct them all together. And then for each of those that we form, so let's say it was both of these rows, it was this one and this one. So we're going to make that into a true. So we're going to apply case 2 for each of those rows. So we get P and P prime in our first conjunction. And then in our second one, we're going to get not P and P prime like that. And then what the second line says to do is form a disjunction of all of these conjunctions. So what we do in that case is take each of our conjunctions. So we just have 2, P and P prime. And then we're going to put or this time because we're forming a disjunction of all of these conjunctions. Not P and P prime. And so basically by following this, for any truth table or any truth function that anyone can give us, we are able to construct a formula using just the connectives not and or. And so that means that they are expressively adequate. Okay, so here's some more examples for us to go over. So in this first example case, which you can see is clearly, just negation. Well, what are we going to do? Well, we're going to go across. We've only got our one row, which is true, and that's this one. And so we're going to just go across it and read it, and we just assert P, okay? And that is that done. Now, what do we do in this second case? Well, we've got truth here, we've got truth here, and we've got truth here. So what we do in this case is we're going to go across our first one and just read it off. So we have, P and Q and R. And then in this case, we have P and Q and not R. And then in this case, we have not P and Q and R. And then we're going to just disjunct all of those together. So we get P and Q and R, or P and Q and not R, or not P and Q and R. So I hope that makes sense at that point. And then here we have a truth table where everything is false in our function column. So in this case, what we are going to do is we're going to just assert P and not P, so that's a contradiction, and Q, and be done with it. So there are some examples for translating truth tables into disjunctive normal form. Okay. So what about the expressive adequacy of other languages that we might have that can consist of different sets of connectives? So, for example, take a second language that consists of not and the hook for if-then for material implication. Well, as we know that this set is expressively adequate, if we can translate every well-formed formula in this set into our second set, then that means that the second set is also going to be expressively adequate. So all that we have to do then, once we've proved the expressive adequacy of not and or, is go on to show that there is a translation between the two languages. So we can do that as follows here. So any truth table which includes conjunction has the same truth table as a formula without the conjunction connective, including only the connectives from this language, so not and the hook. So here's the following equality. A and B is the same as, that's a metalinguistic, defining symbol, not A, then not B. Okay, so any formula, including that symbol, the and symbol, can have its occurrences of and systematically replaced, preserving its truth table. So if we have any formula in which there are occurrences of and, we can go through and systematically replace occurrences of and with these connectives. I mean, I suppose they sort of stay the same, but systematically just replacing the way that the formula looks like that, and the truth table will remain exactly the same. Okay, and then we show that we have the same thing for OR and our two connectives here. So we have this equality between the two, and it's just the same. We can systematically go through, and any formula in which OR occurs can have all its occurrences of OR systematically replaced, preserving its truth table. And so by carrying out the above replacements for every formula that might occur in our first language, which is this one, by carrying those out, we show that any formula in L1 can be expressed in L2. Every formula in L1 can be expressed in L2. So if L1 is expressively adequate, meaning it can express any truth function, then L2 is also expressively adequate and can also express any truth function. So hopefully you can see why that is. Okay. So how about if we only had one connective? So our language here, has had two connectives. The language above had three connectives. When I first introduced the language that I first introduced had five connectives. It had all of these, but what I'm just showing here is that you only really need these three, or you only really need these two. The reason that I introduced all of them is because if you're learning logic, you'll come across all of them. So it's good to have a definition for all of them. So that's the reason why I, defined them all in our language here. But obviously, if we have a smaller number of connectives, if we only had not and or if we only had not and the hook, well, then we'd have fewer cases to do when it came to our proof by induction. So having fewer, having an expressively adequate language with fewer connectives is probably going to be desirable if we're doing those sorts of proofs. But we could even have fewer connectives. So there are languages which include only one connective, which are expressively adequate. The first person I'm aware of to talk about this is C.S. Peirce, but perhaps other people did before him. I'm just not aware of that. And also H.M. Scheffer in 1912 has proofs of the same thing. And these two connectives are this one, the NOR, so you can see the truth table for NOR, which is this. And you can see that there's a translation between not and. And so because you've got that translation between not and, you can have, and because not and is expressively adequate, you can have that translation, you can have just the connective of the downstroke. Downstroke sounds a bit strange, but you can have just the connective of the downstroke in an expressively adequate language. And then you have this symbol, the Scheffer stroke. And it is expressively adequate also. You can see that that's not and. And similarly, they're kind of like the dual of each other. So even though not a is the same for both of them, you can see that this one that's joined like this, that's and in that case, and that's or in that case. So that gives you a little bit of insight into the difference. But if you want, if you're following this along and you want a little bit of a stretch, to test some of the things that you've learned, then I would recommend, coming up with the proofs of expressive adequacy for the Scheffer stroke and the downshift arrow by coming up with the proof and writing out the translations like we sort of did here as well. Okay, so that is going to be all for today. I'm thinking in the next episode I'll probably move on to showing some different proof systems, which is what I was thinking of doing here. And then I think after that, we'll talk about soundness and completeness, and perhaps compactness, before moving on to quantified logics. Yeah, that sounds about right. Then after quantified logics, maybe we'll have one video dedicated to talking about, the conditional and arguments for and against translating it in particular ways. And then after that, we'll move into modal logic, where I think we'll start with K and move into S5. I'm not sure what we'll do at that point, but I'll probably keep the thing going, and we'll have soundness and completeness proofs to cover as well in each of those languages also. Maybe we'll do a bit of set theory and talk about the relationship between set theory and logic, so that there's a sort of isomorphism between them and why that is, and maybe the same with probability theory. Oh, and also some electronics, I was thinking. So we can talk about adding how computers add numbers together and do arithmetic and stuff like that. I think that could be quite fun as well when we get there. So if you're interested in that, stick with the course and we'll get there eventually. Otherwise, thank you for watching. If there's something that you do want to see, let me know in the comments, and leave a like if you enjoyed it. See you in a bit, guys.